The Harrier jump jet gave pilots a superpower and then spent the next decade reminding them it could take it away in seconds. The same jet that terrified the Soviets is happy to take the life of its pilots if they are sloppy during landing. It was May the 5th, 1969. People in London woke up to something strange. A combat jet is randomly in the middle of the city. But that was only the beginning of their surprises. The jet lit up its engine, lifted like a helicopter, and headed to New York. What they just watched was a vertical takeoff from a fixed-wing jet. Today, we've seen the F-35 and all kinds of engineering party tricks, but in 1969, the Harrier might as well be black magic. And for the people who'd paid to develop it, that was exactly the point. The Harrier was built to fight a war where runways might not exist. To better understand how they got here, let's look at the context behind the story. In the 1950s, Western Europe looked tiny next to the army, the Soviets parked on the other side of the Iron Curtain. Looking at that, NATO knew the Soviets might be tempted to flex their muscles, so they basically said, if you roll west, we go straight to nukes. That got written down as massive retaliation in a 1954 paper called MC-48. Then the Americans started scattering nuclear bombs all over air bases in Western Europe. From Moscow's side of the scope, that looked like this. If anything kicks off, NATO jets and missiles launch nukes at our armies from bases right on our doorstep. So their planners asked the obvious question, how do we make sure nothing ever gets off those runways in the first place? This is still before ICBMs are routine, so if NATO wants to hit targets deep in the Soviet Union, it has to launch bombers off runways in Europe. So the Soviets think, if we just take away the runways, we take away the threat. By the mid-50s, they'd started building a whole tool set around that idea. They brought in tactical nukes and short-range ballistic missiles that can smack targets in West Germany from inside the Warsaw Pact. Then they forward base all of that in East Germany, Poland, and Czechoslovakia, where the ring on the map for their range falls neatly over NATO runways just across the border. Western intel watches the basing, the parades, and gets enough from spies to put two and two together. Those nukes and strike jets are meant to hit airfields first, especially the ones with nukes on them. Then, NATO simulates the whole thing in the 1955 carte blanche war game in West Germany, and realizes that if both sides ever actually fire the weapons they're building, the Soviets will first wipe all runways, making it difficult to launch any counterattack. That realization sends a shockwave through Western military planners, and they start scrambling for a response. Their simple answer on paper is basically, the Soviets think they've got us in a chokehold by going after our runways, so let's take runways out of the equation. Instead of vulnerable concrete being the heart of our strike and nuclear plan, what if we build strike jets that don't need it? NATO turns that idea into a formal shopping list called NBMR-3, short for NATO Basic Military Requirement 3. Inside it is a request for a new kind of jet, a vertical, short takeoff and landing strike aircraft that can cruise close to Mach 1 at low level, haul roughly a 2,000-pound weapons load, and still give you around a 250 nautical mile combat radius from little dispersed strips instead of big, full-length runways. By the time this requirement went out in the early 1960s, Britain already had a head start. At Hawker Siddeley's Kingston office, Sidney Camm's old fighter design team had been quietly working on a different kind of aircraft with engineer Ralph Hooper, and down the road at Bristol, a small engine group had come up with a vectored thrust power plant that could swivel its exhaust. That combination became the subsonic P.1127, effectively a flying test rig for the idea of a jet that could lift itself on its own thrust. NBMR-3, though, was asking for more than that. NATO wasn't just after a neat hovering demonstrator, it wanted a supersonic vertical short takeoff and landing strike aircraft. Britain's official answer to that specific NATO competition wasn't the P.1127, but a new, more ambitious design, the Hawker Siddeley P.1154. France looked at Mirage-based VTOL concepts with multiple lift engines. Italy pushed its Fiat G95 ideas, other nations had their own paper projects. On the drawing boards, it looked like there might be several ways to solve the no runways problem. The trouble was that most of those designs tried to bolt VTOL capability onto conventional high-performance fighters, by adding separate lift jets or complex mechanisms. That made them heavy, maintenance-hungry, and vulnerable. If one lift engine failed in the hover, you didn't get a warning light, you got a roll and a crater. As the studies went on, it became clear that turning these supersonic projects into practical, everyday squadron aircraft was going to be far harder and more expensive than the brochure suggested. Then, the politics and bureaucracy kicked in. Each major NATO country naturally preferred to back its own aerospace industry. Opinions split over which design should win, and no consensus ever really formed. Without a clear favorite, and with cost and complexity rising, NBMR-3 was eventually cancelled. The supersonic P.1124 died with it, and there was no single NATO standard vertical takeoff and landing strike fighter. What Britain did still have, though, was hardware that actually flew. The P.1127 had already proved it could hover and transition, and a slightly more developed version, the Kestrel, had been evaluated by a tripartite squadron from the UK, US, and West Germany. It was subsonic and far less glamorous than the P.1154 paper fighter, but it was real, it worked, and it fit the original Cold War problem very well. A jet that could disperse away from big air bases and still deliver weapons on target. So when the NATO competition collapsed, London stopped chasing the supersonic ideal and doubled down on the machine it could actually field. The RAF ordered 6 pre-production P.1127 in 1965 to see how VTOL would fit into everyday squadron life. These weren't frontline fighters yet, they were flying test beds for procedures, tactics, and training. The experiment went well enough that, in early 1967, the RAF followed up with a production order for 60 aircraft. That was the moment the jet finally got its famous name. The Kestrel label disappeared, and the P.1127 family entered RAF service as the Harrier. The Harrier was a compact but powerful machine, about 25 feet of wingspan, 11 feet tall, and 47 feet long. It could reach around 731 miles per hour, just under the speed of sound. Getting from those early P.1127 sketches to an operational Harrier force was not cheap. By the mid-1970s, Britain had sunk very substantial sums into Harrier and related vertical takeoff and landing work, the sort of money that translates into a multi-billion-pound program in today's terms. For that kind of investment, you'd expect something special, and most of that special lived in the engine. The vectored thrust Pegasus engines is brutally powerful, even by today's standards. To get a sense of scale, look at another famous jet from around the same era, the McDonnell Douglas Phantom, powered by the GE J-79. Each J-79 in dry power produced roughly 11,900 pounds force of thrust. A single Pegasus in the Harrier, by comparison, could push out around 23,800 pounds force, almost double. On paper, that sounds like overkill, but in reality, every bit of that thrust was needed. A conventional jet only has to accelerate down a runway until the wings are moving fast enough through the air to generate lift. In that phase, the engines are mainly fighting inertia and drag. The wing and the airflow together are doing the job of holding the aircraft up. A Harrier trying to lift off vertically is in a totally different situation. There's no runway roll, no long takeoff run to build up lift. The engines aren't just pushing the aircraft forward, they are literally holding up the entire weight of the jet on a pillar of air. So now the engine has to overcome inertia, drag, and gravity directly. And that was only one piece of the puzzle. The next big question was, how do you make a jet do vertical takeoff and landing reliably and controllably, not just once for a test, but every day in service? To explain how they solved that, we need a very quick, simplified tour of how a normal jet engine works. At the front, you've got the intake, the big opening you see on airliners. Behind that are rows of rotating blades that compress the incoming air, squeezing it into a smaller volume and raising its pressure. That high-pressure air then moves into a chamber and is forced through narrower passages. According to Bernoulli's principle, as the passage gets narrower, the air speeds up. At this point, fuel is sprayed into the fast, high-pressure airflow. It burns, and the expanding gases rush out of the back of the engine. That high-speed jet of exhaust is what produces thrust. Most jet engines follow that basic pattern, with variations. The Pegasus took that same core idea, but used it in a different way. Instead of having one big exhaust nozzle at the back, it split the thrust into 4 separate nozzles, spaced along the sides of the fuselage. On a Harrier in normal forward flight, those nozzles are rotated to point backwards, just like a standard jet exhaust, pushing the aircraft forward. For vertical takeoff or hovering, the pilot rotates the nozzles to point downwards, so the engine blasts air at the ground, and the reaction force pushes the aircraft up. But as soon as you try to hover, another problem appears. In normal flight, you control the aircraft with moving surfaces, ailerons, elevators, rudder, sticking out into the airflow. You tilt those surfaces into the slipstream, the airflow over the wings and tail changes, and the aircraft pitches, rolls, or yaws in response. The key point is that all of this depends on having enough air flowing over the surfaces. When a Harrier is hovering, there isn't a strong forward airflow over the wings and tail. The main airflow is straight down from the nozzles, so the usual control surfaces become far less effective. From a control systems point of view, a hovering Harrier starts to look more like a small spacecraft than a normal airplane. It's hanging in space, supported by its own thrust, and you can't rely on traditional aerodynamic controls. Once the engineers realized this, they borrowed thinking from the spacecraft world, particularly from the Apollo program's reaction control systems. They added a separate control system that bled high-pressure air from the engine compressor and piped it out to small jets, reaction control valves, at the nose, tail, and wingtips. When the pilot wanted to roll in a hover, the system would puff more air out of one wingtip jet than the other, creating a rolling moment. To pitch up or down, it would use the nose and tail jets. In other words, in the hover regime, the Harrier behaves like a spacecraft with little thrusters controlling attitude, while the main nozzles take care of lift. Those are the key tricks that made the Harrier technically possible. Huge vectored thrust to lift the aircraft, and a reaction control system to keep it pointed where the pilot wanted while hovering. There were many other refinements and improvements over the years, but these are the core ideas. Of course, that doesn't mean the aircraft was perfect. Even after decades of service and multiple redesigns, one of the Harrier's most serious weaknesses was how twitchy it could be during vertical or very short landings. Think about the physics of what's going on in the landing phase. The jets are pointing downwards, pushing a huge mass of high-speed air at the ground to keep the aircraft in the air. As the Harrier gets close to the surface, that jet wash hits the ground, spreads out, and then starts to swirl back up around the aircraft. That disturbed air is turbulent and uneven. Any sudden change in the airflow under one side of the aircraft can kick it into a roll or pitch oscillation. And sometimes it turned deadly. The interaction between the jet wash and the ground could set up rapid oscillations in attitude that escalated faster than a human pilot could counter them. In the worst cases, the aircraft could suddenly tip, lose lift on one side, and slam into the ground before the pilot had time to recover. Many of these accidents were unsurvivable. One workaround pilots were given was essentially to commit to the drop, cut the thrust a few feet above the surface, and accept a firm touchdown, rather than trying to hover delicately in the most unstable zone near the ground. That sounds crude, but it reduced the time spent in the most dangerous part of the flight envelope. As onboard computers improved, engineers added flight control systems that could help stabilize the aircraft in the hover and during vertical landings, reacting faster and more precisely than a human could manage alone. This significantly reduced the number of loss of control accidents, but it never entirely eliminated the risk. The physics of blowing a massive jet of air at the ground and balancing on it is unforgiving. After years of testing and tweaking, by the end of the 1960s, the Harrier was finally ready to stop being a science project and start doing a job. In April 1969, No. 1 Squadron became the first unit in the world to be equipped with Harriers. Almost immediately, it got a chance to show off what made it different. In May 1969, one of the squadron's Harriers took part in a transatlantic air race from London to New York. The race started at the London Post Office Tower, with pilots racing down to St. Pancras, jumping into their aircraft, and then flying across the Atlantic to the Empire State Building. The Harrier didn't win because it was the fastest jet in the air. It won because it could land much closer to the finish. While other aircraft had to go to conventional airports and rely on transport in and out, the Harrier could simply drop into a spot in the city itself. For people in New York who had never seen a Harrier before, watching a jet fighter come in and land like a helicopter in the middle of the city would have been a jaw-drop moment. The fleet then started to grow. In 1970, 2 more RAF squadrons in West Germany received their first Harriers. The Harrier's first big test in combat came in 1982 during the Falklands War. After about a decade of relative peace and training use, the UK decided to deploy RAF Harriers alongside Royal Navy Sea Harriers for the campaign. The RAF aircraft were upgraded to work better at sea, operating from carriers and makeshift decks, and sent south with the rest of the task force. Between the 2nd of April and the 14th of June 1982, Harriers flew more than 2,000 sorties. They provided air defense, ground attack, and reconnaissance. 10 Harriers were lost in total through a mix of ground fire, accidents, and mechanical issues, but overall they proved that a small VTOL fighter could deliver real combat value a long way from home. If we jump forward to the early 1990s, we find the Harrier involved in another major chapter, the Gulf War. By 1990, the US Marine Corps had adopted the Harrier, but it was still seen by some as an unproven, slightly oddball aircraft. When Operation Desert Storm began, the Marines initially held their Harriers in reserve, ready to be used if needed, but not thrown straight into the heaviest fighting. That caution didn't last long. As the operation unfolded, Harriers were tasked with more and more missions. By the end of the war in 1991, they had flown over 3,350 sorties and accumulated around 4,100 flight hours. The way they were used also looked different from how the RAF had employed them. While the UK tended to use Harriers mainly for close air support, the US Marines leaned into the jet's flexibility. Their Harriers flew bombing missions, resupply runs, close air support, and even some air-to-air engagements against Iraqi fighters. Against Iraqi MiGs, the Harrier was not the faster or more agile aircraft in a classic dogfight sense, but it had one party trick the MiGs didn't: vectored thrust. Marine pilots developed a tactic known as dumping speed. By swiveling the nozzles forward briefly, they could brake very hard in the air, causing a chasing enemy to overshoot. Once the opponent flashed past, the Harrier pilots suddenly had the better position, now behind the target with a clear shot. Through the 90s and 2000s, the world around the Harrier was changing faster than the jet could. The nightmare it had been built for never arrived. Instead, Western airpower found itself fighting very different wars. Long campaigns over Iraq, Afghanistan, and the Balkans, launched from big, secure bases and large-deck carriers that weren't under immediate threat of being turned into rubble. In that environment, the Harrier's party trick came with a bill. Vertical or short takeoffs hammered the fuel reserves and payload. The engine and nozzle system were maintenance-intensive, and the hover and landing regime stayed unforgiving, even after better controls arrived. For every hour a Harrier spent over the battlefield, there was a lot of manpower, money, and risk tied up in keeping that capability alive. At the same time, conventional strike jets got better at doing the Harrier's favorite jobs without any of its weirdness. Aircraft like the F-16, F-A-18, and Tornado could cruise faster, carry more, and plug into increasingly sophisticated sensor and weapons networks. Precision-guided munitions meant you didn't need to hide jets in every woodline. You could launch standoff weapons from well-protected airfields hundreds of miles away and still hit a single vehicle or bunker. The Harrier's original selling point, we can keep flying even if the main bases are gone, mattered less in a world where the main bases weren't under the kind of existential threat planners had imagined in the 1960s. Meanwhile, its weaknesses stayed. It wasn't the fastest, it didn't have the longest legs, and it had no stealth. It was a specialist tool in a toolbox that was slowly standardizing around multi-role, easier-to-support platforms. Then there was the budget reality. Running a small, unique fleet is expensive even if the aircraft are simple. As defense ministries started asking hard questions after the Cold War, how many different jet types do we actually need? The Harrier was always going to be near the top of the list of candidates for retirement. For the US Marines and the UK, the final push came from the next generation. The F-35B promised something Harrier could never offer: a short takeoff and vertical landing aircraft with modern sensors, stealth, and a design built from the start to live in a networked battle space. On paper, it could do the Marine Corps jump jet mission and the classic strike fighter role in a single airframe, and it did it with far more growth potential than an already aging Harrier airframe. That doesn't mean the Harrier was a failure. Operationally, it proved that a vertical short takeoff combat jet could be more than a science project. It fought in the Falklands, in the Gulf, over the Balkans, and in Iraq and Afghanistan, and it gave its operators options they would not otherwise have had. What killed it wasn't that it couldn't do the job, it was that the job changed, and newer designs could cover the same missions with fewer compromises. In the end, the Harrier is one of those aircraft that did exactly what it was asked to do, only to be made redundant by the disappearance of the war it was designed for and the arrival of cleaner, more capable machines. It started life as a workaround for a Europe full of cratered runways and finished it flying in a world of stealth jets, precision weapons, and giant, floating air bases. In that new world, its trick was still impressive, it just wasn't worth the price anymore. So that's it for today's video. Don't forget to like, subscribe, and ring that notification bell. It goes a long way for us.